I got it.
Okay, so in the second part of the period, what I want to do now is I want to go over the bonus, which is going to help you with the problem on the lab. Now the lab is going to be due on Monday. If you're in school, I want you to go ahead and just bring the lab. You don't have to submit it online. Only those that are full-time virtual need to submit it online. Okay? But if we look at this problem right here. This is what's coming later today. So we want to look at this problem. Because this bonus is like the problem on the lab. This is not on the AP test anymore, but I think it's still just a good problem to know how to do. So we have a beaker. In this beaker, we have some I- floating around, and we have some CO3 2- floating around. We're going to add in lead. And then lead iodide and lead carbonate are both going to want to form. Question is, which one's going to form first? Okay? So we use the KSPs. Now the KSPs are given further up in the problem. So the KSP of PBI2, does anybody still have a test? KSP of PBI2 is, I gotta go to the previous page. KSP of PBI2 oh, there it is, right there at the top, right there. 8.7 times 10 to the minus 9. And the KSP of lead carbonate is going to equal 1.5 times 10 to the minus 13. Now it does seem like we could just go well, this is the smaller one, so this one's going to precipitate first. But this one is going to be equal to the concentration of the I-. They have different concentrations, number one. Number two, this is going to be, because this is going to break up into 2 I-, it's going to be PBI2 squared, iodine squared. So I know I'm going to calculate my PV. We want to find out which one requires the least amount of lead to cause a precipitate. So we're going to solve for lead. That's where my iodine is coming from. The iodine is not coming from the PBI2. The iodine is coming from sodium iodide, so we don't multiply by 2. But the iodine concentration is 0.1. But because it's PB goes PB2 plus 2I-, we got to square that. So then it's just going to be divided by this, so it's going to equal 8.7 times 10 to the minus 7. That's the concentration of lead that's going to cause the PBI2 to precipitate out. Do the same thing for the carbonate, except this time it's 1-to-1. PB2 plus, and the carbonate is 0.15. So we divide 1.5 by 1.5, we end up getting 1 times 10 to the minus 12 molar PV for this one. Since this one is the smaller value, it precipitates first. That's what you needed to show to get the bonus. See, this one is PbCO3 goes to PB2 plus CO3 2 minus. Okay, now, second part. You have to do this on the lab as well. Now, the only thing different between this problem and what you have, the one that you have to do on the lab, is that to get these concentrations, you first have to do the dilution. Because you're adding 100 milliliters in 1 milliliter. So it's not going to dilute much, but it is going to dilute some. So we have to do the dilution to get these concentrations, and then you just plug them in and do exactly the same thing. Now, what we want to know is, okay, what is when the first one, this one's precipitating first, this one's second. What is this carbonate concentration when the lead iodide begins to precipitate out? Well, the lead iodide is going to precipitate out when the lead is 8.7. So I'm going to still use this one, because I'm still interested in the carbonate ion. That's what the question's asking for. So 1.5 times 10 to the minus 13 is going to equal my lead at 8.7 times 10 to the minus 7. Well, what's the carbonate going to be when the lead is that high? Well, just divide it out. Maybe I'll still have your test. 1.7 times 10 to the -7. Thank you. So that's the carbonate amount that remains when the lead iodide begins to precipitate out. So there's very little of this left. Almost all of it's precipitated out. Now if we want to do percent CO3, 2 minus remaining, what do I do? Question didn't ask for this, but what would I do if I wanted percent remaining? What part? This is what's left. 1.7 times 10 to the minus 7 divided by the whole, well, we started with 0.15. And we get 1.1 times 10 to the minus 4th percent CO3 2 minus remains. So not very much. What is 10 to the minus 4? That's 10 thousandths. So 1/10,000th of a mole per liter. So there's not much left in there. So that's what you have to do for that. So if you're not finished with your lab, you can finish that over the weekend, turn that in on Monday. Okay? But this should help you to be able to do that problem. Again, the only difference is you have to do the dilution to get these. And that's just going to be 100 over 101 times the concentration. Or 1 over 101 times the concentration. We all good? Any questions on that? One other one that I wanted just to kind of highlight, and I forgot to do, is this one right here, will a precipitate form? And this one was kind of the reason why there was a little bit of a curve as well, because I felt a little guilty on this one because we never did a problem like this, okay? Exactly. So we have 75 milliliters added to 100 milliliters. So for my MgI2, it's going to be 75 over 175 times my concentration of 0.0050. So what does that come out to? I think it's 0.00214. MgI2. Now, but we want the iodine. What's this going to break up into when it dissolves in water? 2 I minuses. So the I minus concentration is going to be 2 I minus for every 1 MgI2. So we're going to end up with 0.00428 molar I minus. That's what you have to put into your KSP. A lot of y'all just use the 0.0214. I think I should only taken like a 1 point off if you did that, just because it was a real low minor. It didn't change the overall answer. It's just, you need to know to multiply that by 2 because the source of the iodine is MgI2. Then the rest of it So you always got to look at what's the source of the ion that I'm putting into the solution. How am I getting there? All right, any questions on any of that? Good deal. All right, now, normally, I would be going into electrochemistry at this point. Okay, that's my general thing, and then we finish with acids and bases, but we only have 2 weeks between now and spring break. I don't want to have a long break, and I want to just kind of get into acids and bases and then be able to finish with electrochemistry the first week we kind of come back, okay? I don't think I'll really be able to get acids and bases fully in the 2 weeks. We may have to take another week, so, but I want us to try to have 3 weeks of review. All these snow days and e-learning days are really kind of, they cost me a week. So I'm trying to kind of figure out a way to catch up. So we're gonna do acids and bases, then we're gonna finish with electrochemistry, then we're done. Okay, so there's a light at the end of the tunnel, okay? And I don't think it's an oncoming train. So we should be okay. You never heard that? No. I see a light at the end of the tunnel, I just hope it's not an oncoming train. Get your hopes up and then bam, you just get smashed. That's kind of the way things happen. All right, so let's talk about definitions of acids. And notice I'm saying plural because we're going to have, this is chapter 16. Definitions of acids and bases. Anybody remember any of them? pH is what we're going to measure as far as doing, how acidic something is. But by definition, there's different people's names.
Are you talking about the person's name? I thought it was just a disassociation.
Is it like if it's a donor?
Yeah, that's the second type that's going to be there. But the first one is going to be the Arrhenius definition. The Arrhenius definition, named after Svante, S-V-A-N-T-E, Svante August Arrhenius, a Danish chemist who did a lot of work with how substances dissolve as ions, electrolytes. And so this definition is probably the most common and the most widely used, and it's the one that we're going to use for all pH calculations and everything. So it's the one we've been using as a definition all year long. So what ion do all acids have?
H+.
H+, right? So an acid is going to be any substance that increases the H+, or we can say the H3O+ ion concentration. In water. Okay? Now, H+ and H3O+ are 100% synonymous. If we look at a water molecule, it looks like this, but when you put an acid into it, acids are the only covalent compounds that ionize in water. Most covalent compounds, sugar, alcohol, ethylene glycol, anything that dissolves in water that's a covalent substance, they're going to dissolve as neutral molecules, non-electrolytes. But acids are the one covalent compound that actually ionize in water. So when you put an acid into water, the H+ is pulled off by the water, and we form that coordinate covalent bond where both electrons come from the oxygen. The H+ is just drawn that's very polar. Remember, oxygen's negative. So there's a strong attraction for that H+ to the water. So an H3O+ is nothing more than a hydrated H+. Okay? And does anybody remember the name of the H3O+ ion?
Hydronium.
That's the hydronium ion. Okay? H+ is simply going to be the hydrogen ion. can use H plus, H3O plus interchangeably, synonymously. They have, the pH can be the pH is negative log of H plus or the negative log of H3O plus. Doesn't matter which form you use. Okay? So what's the base gonna be?
Any substance that increases the OH minus.
That's exactly right. Say that again loud enough.
Any substance that increases the OH minus.
The OH minus. Acids are H plus, bases are OH minus. Okay? So acids generate H plus, bases generate OH minus. Acids neutralize bases because the H plus from the acid combined with the OH minus from the base, making neutral water. That is your most common, most widely used, this is the definition that we'll use for all of our, again, all of our pH problems. Now, one thing as we go through all these definitions, they're not going to contradict one another. So when I go to the next one, if it's an Arrhenius acid, it's going to be a Bronsted-Lowry acid. It's going to be a Lewis acid. They're not going to contradict. One's not going to be an acid by one definition and a base by the other. So the second definition is a Bronsted really, because it has an umlaut, Lowry. Just kind of like Leibniz and Newton, both theoretically, supposedly, created, came up with, invented calculus, but Newton published first, and so he gets credit for it, but they both kind of did it independently, but at the same time. Bronsted and Lowry were not working together. They're two independent scientists, but they came up with this definition together, so they both get their name on the definition. This is the one that Usman, you were talking about. This is where we talk about a hydrogen donor and a hydrogen acceptor. So an acid is an H plus, which sometimes we refer to it as a proton donor. Why would H plus be called a proton?
It's one proton only.
Because how many electrons does it have?
0.
0, right? So a hydrogen atom is one proton, one electron. You take the electron away, all you have left is a proton. So a lot of times we'll talk about a proton donor, a proton acceptor. A proton is an H plus. And a base is going to be an H plus acceptor. So notice now we don't have anything to do with OH minus, and it doesn't have to be in water. But if I look at just your standard HCl plus H2O, okay, it's going to go and make H3O plus Cl minus. And what type of acid is HCl, strong or weak?
Strong.
So what does that mean?
Ionizes completely.
Ionizes completely, so it's almost all product. So the Ka, the equilibrium constant for this acid is going to be super high, almost infinity, okay? Because the denominator is approaching 0. So it's a super high, so it's going way to the products. But according to the Arrhenius definition, it's an acid because it's producing H3O plus. But Bronsted just looked at it from a different perspective. Rather than looking what it made, let's look at the reaction. You see, perspective is very important. Just think about a bacon and eggs breakfast. The hen can be very dedicated to making that perfect egg. But the pig's gonna have a little bit different perspective on that breakfast. He's gonna be totally committed to that bacon and eggs breakfast. We're looking at the same thing, just from a different perspective. It's the difference between being dedicated to something or being totally committed to something. Okay? I heard that at an athletic banquet one time. The difference between being dedicated to your sport and being committed to your sport. Okay? Anyway, I always think it's funny, so I can't look for an opportunity to bring that up. Okay? So, we're gonna just look at this from a different perspective. Rather than looking at the products, we're going to look at, well, how is this HCl changing to go to here? Well, it is donating the hydrogen to the water. And in an Arrhenius, water is just in the reaction, but I mean, it's just where the reaction is taking place, the medium. Whereas here now, if this is donating the hydrogen, that makes this the acid. What does that make water?
The base.
The base. So in this case, water's a base. It's obviously a weak base, but it is indeed a base. The acid kind of forces it to take the hydrogen. Now, this reaction is reversible, which means it can come back right to left. So if I'm looking right to left, what's happening with the hydrogens? Going this way, how is this becoming this? Or pardon me, this becoming that?
H is going to.
It's donating the hydrogen to the chlorine, right?
Yeah.
What does that make that?
That's the acid.
An acid, but we call it the conjugate acid. Good. And what's Cl minus going to be called?
Conjugate base.
The conjugate base.
What does conjugate mean?
Okay, good question. Beat me to it. If you've taken a foreign language, you have to conjugate the verbs, right? A star, estoy, estás, está, estamos, están. Okay? Estáis. I never did learn all those weird ones. I always just did the basic ones. Okay? My Spanish is very limited. Got myself in major trouble in Costa Rica when I was trying to communicate, but I survived. Got made fun of a lot, but I survived. But when you conjugate a verb, it's different forms of the same verb, right? They're all related to one another. H3O plus and H2O are different forms basically of the same thing. So it's the thing that's related to it. That's what the conjugate means. It's related to that thing. So the H3O plus and the H2O are kind of the same Latin root word, so to speak, of H2O. And so they're going to end up being the conjugate. So HCl and Cl minus, those are the two things that are related, from the same thing, same stem. And so this is your acid with the conjugate base and a base with the conjugate acid. The conjugate is the species that remains after an acid donates a hydrogen or after a base accepts a hydrogen. Conjugate acid. The species, the thing, the species that remains after a base accepts an H plus. So what's a conjugate base?
Species
Okay? The species that remains after an acid donates an H plus. So in this case, what's this acting like? Because it's donating the hydrogen, right? So this is my acid, and it's always this hydrogen. We're going to learn why later on this unit, but this hydrogen is the one that's going to get donated, the one it's because it's the most polar, because oxygen's stealing the electrons away. So that makes it very positive, makes it vulnerable for the very polar water to pull it away. Okay, which makes water again the base. So what does that make this? Conjugate base, and this is the conjugate acid. So, these two and these two are what we refer to as conjugate acid-base pairs. It's the acid with its conjugate base or the base with its conjugate acid. These two are not a conjugate acid-base pair. These two are not a conjugate acid-base pair. Conjugates means they're related to one another. They're from the same basic thing. Okay? So it's always going to be one from each side of the equation. Conjugate acid-base pair. Now, if this is a strong acid, ionizes 100%. What does that mean about Cl minus's attraction to get the hydrogen back to come here?
Most zeros.
Very, very near zero. It's very, very low. So this is the conjugate base here is very weak. The chlorine is basically saying we're never, ever, ever, never, ever, ever getting back together again.
Taylor Swift.
Okay? Yeah, we ought to write a song about it. And so, never, ever getting back together again. So a strong acid makes a very weak conjugate base. On the other hand, this Ka, the acid constant, is 1.8 times 10 to the minus 5 for acetic acid. So what does that mean in terms of product favored, reactant favored? Very reactant favored, right? Very little product. So in other words, most of it wants to be in this form. So when the acetate ion here is in water, it has a strong attraction. It would much rather be in this form than in this form. That's what the K tells us. So therefore, this is a weak acid. This is going to make a much stronger conjugate base. So it's opposite. Acids make conjugate bases, bases make conjugate acids. The stronger the acid, the weaker the conjugate base. The stronger the base, the weaker the conjugate acid. Acids make bases, strong makes weak. If we look up here at this acid-base chart, if you look up here at this acid-base chart, you can see your strong acids up at the top. Now notice it says acid, HB, any H plus a B minus, a base. A lot of times they say HA for the anion, okay? And then you get B minus for the base. So you have your acid and then the conjugate base over on the right. Y'all seeing that? So over here we have very strong acids, but talking about the base, they're very weak conjugate bases. You seeing that? So strong acids here, the conjugate is a very weak conjugate base. But as you go down, the strength of the acid is decreasing, but the strength of the conjugate base is increasing. So the less the acid wants to donate the hydrogen, the more the base wants to get back into that molecular form and not be in the ionic form. Whereas you come all the way down here, ammonia, it's an incredibly strong base. It doesn't, ammonia wants to go to NH4, it doesn't really want to go to NH2. So that NH2 minus is a very strong attraction for another electron. Okay? So, acids make bases, bases make acids, strong makes weak. So, let's just look in your book. Chapter 16. I'm on page 717. Page 717. Looking at the question down here at the bottom, number 17, on page 717. So we want to designate these as an acid or base, Bronsted acid, Bronsted base, conjugate acid, conjugate base. So how's the NH4 plus changing to become NH3? losing, it's donating a hydrogen. What's it donating it to? The Cn minus. So this is the one donating, this is the one accepting. Acid, base. Now after the acid donates and becomes NH3, that makes this, now it has the ability to accept one back, so it becomes the conjugate base. This one now has a hydrogen that it can donate, so it's the conjugate acid. So what are my two conjugate acid base pairs?
NH4 and NH3.
NH4 plus and NH3,
Cn minus and HCN.
okay, and these two. Are we all good with that? So you can do, what about this one? This one's a little bit more complicated. Which one's donating a hydrogen here?
The H2O.
The water, right? So what does that make water acting like?
A base.
Acid.
Wait.
An acid. It was a base in the last one. Here it's an acid. Fancy term. Water is amphoteric. A-M-P-H-O-T-E-R-I-C. Amphoteric. Meaning it can act as an acid or a base depending upon the conditions. You ever heard of, bicarbonate? You're supposed to drink soda if you have an upset stomach. A lot of times you have an upset stomach because it's too acidic, maybe you get a little reflux going, but it's just too much acid. But they say drinking a cola or drinking a 7-Up sometimes will help settle that stomach because the carbon dioxide is the fizz, it actually forms bicarbonate, the hydrogen carbonate ion, HCO3. Well, when you have an ion that has a hydrogen on it, it's amphoteric. It can go either way. It can donate that hydrogen. If it's in a base, it can donate the hydrogen and go to CO3 2-. But if it's in an acidic solution, it can accept the hydrogen and act like a base and go to H2CO3. So it's kind of a buffer. Your blood, we're going to read about this later on, but your blood has a bicarbonate buffer in it to kind of keep the pH of your blood system all just pretty constant. Because if your pH changes by more than 0.2, your organs start shutting down.
Can multiple reactants act like an acid? Like two of them can act like a acid?
You have two acids in here? No, because some,
if you had like
you got to have a giver and a taker.
No, but can you have two givers and one taker?
Oh yeah, I'm sure.
Okay.
They just fight it out. It's, whichever one's going to be the strongest acid is the one that really is going to win that battle.
Okay.
All right, so water is the acid, that makes this the base, so what does that make this?
Conjugate acid.
Conjugate acid, and this is the
Conjugate.
conjugate base. Okay, so if this most likely is obviously we know water is a very weak acid. If it, otherwise we'd drink it and we'd burn the crud out of our throats. Okay, so what does that mean about hydroxide?
Strong base.
We already know that, very strong base. Now, according to Arrhenius definition, this is a base because
It increases the
it generates OH minus. So the two aren't conflicting or contradicting each other. They're just looking at it from a different perspective. Whether or not what does it produce over here versus here. Now, this one right here would not, it's a Bronsted-Lowry, but it is not an Arrhenius acid-base reaction because there's no H+, no H3O+, or OH minus. So that's where the Bronsted-Lowry is just expanding the definition to include a few more things. You don't have to have the H+ and the OH minus for Bronsted-Lowry. Okay? All right, we've got 10 minutes left. I'm going to go to the third definition. Qualifier. Third definition is not on the AP test. However, it's very important, especially when you go to college and you take organic chemistry. Lewis acids and bases, which is the third one, is what they use all the time. Lewis, when have you ever heard about Lewis's name?
Lewis dot structure.
Lewis dot structures. Lewis had a thing about electrons. So Lewis looked at the exact same reactions, but rather than looking at it from the H+ perspective, he looked at it from the perspective of the electrons. In organic chemistry, when you're following these a little bit more complex reactions, they're always following the electrons. And where the electrons are dictating where the lone pair are. So it's always going to be about these Lewis acids, Lewis bases in organic. So I'm going to take 9 minutes and we're going to talk about it, and that's all we're going to talk about it. Probably end up just being a bonus on the test, but I still think it's worth just getting out there so you at least get exposed to it. All right. So, number 3, Lewis definition. A Lewis acid. Again, we're going to look from electron perspective. H plus is an acid by everybody's definition. H plus is always an acid. Oh, are we on over here? Okay? H plus is always an acid. So, what's the only thing H plus can do with electrons?
Get them.
Accept them, right? So an acid is an electron
Acceptor.
pair acceptor, and a base is going to be an electron pair donor. Now, the things that's going to accept an electron are going to be cations cations or H plus. These are all electron deficient. Okay? Whereas, what's an electron pair donor? Anions, or any compound with lone pair electrons. In other words, they're electron rich. Okay, so when we're looking at this, again, we look at the exact same reaction. If I look at this exact same reaction of HCl plus H2O, but I do it in terms of a Lewis dot structure, and then I say plus H2O, what's happening is the hydrogen, Bronsted saying the hydrogen's being donated to the oxygen, to the water. But Lewis said no, the electrons are being donated to the H. Again, it's all just perspective. So as a result, we end up getting H3O plus. And remember, when both electrons come from the same atom, we call that a coordinate covalent bond. It's just like a coordinate, it's just these bonds are exactly the same. It doesn't matter the source of the electron, because an electron is an electron is an electron. But anything that has a lone pair of electrons, you can accept an H plus. You can donate, I should say, you can donate the pair of electrons to the H plus. And then we're going to get, the other thing we're going to have then is Cl minus, and this is H plus. So again, the exact same reaction, just from a different perspective. Now, one final thought on this one is that it expands. Notice now we don't have to have hydrogens, we don't have to have hydroxide, it's all just about electrons. So if I do this kind of strange reaction of, let me do it this way, do it in terms of Lewis dot structures again. Ammonia, NH3, with its lone pair of electrons, it will react with BF3. And what's unique about boron when it's the central atom?
It needs to have 6.
It only has to have 6 electrons, not 8, right? Which means it's got this extra spot right here that can accept a pair of electrons. So the ammonia donates the electrons, and we have kind of like a composition reaction. Where we get this. Now, no way Lewis or Bronsted or Arrhenius call this an acid-base reaction. Okay? Instead, this is just Lewis expanding that definition just a little bit. Just a little, this is called an adduct. When you do a chemical reaction like that, when you put the two things together, that's just over to my information. No, you're not, that's not gonna be on the test. Okay? So if we want to just kind of look at this from, I remember when I was in elementary school or whatever, doing math, we had to have subsets and supersets, and I don't know, we had to do where things intersected. You probably don't do that anymore. It's probably, that was new math then, but now it's old math. But this is your Arrhenius definition. It encompasses most things. But then the Bronsted-Lowry just makes it a little bit bigger. And then the Lewis definition makes it a little bit bigger. Okay? So we end up saying, okay, again, this is an acid by Arrhenius because it produces H3O+. It's an acid by Bronsted because it's donating the hydrogen. It's an acid by Lewis because it's accepting the pair of electrons. Now, I know you guys are ready to put up, but I said I was going to go all the way to the end here. So if we look at this reaction right here, and I want to define which one's the Lewis acid, Lewis base. Which one of these is electron rich? OH minus. That's going to be my source of electrons. It's going to donate, again, notice to the hydrogen, the H plus, the NO2 minus stays over there, so the H plus is coming over here. Now, according to Bronsted, this is an acid because it's donating the hydrogen. Okay? But this is electron rich, so this is my Lewis base. This is the H plus is what's accepting it, so it's my Lewis acid. In this one, again, this is my electron rich. So this is my base. It's going to be attaching to the iron, which is the Fe plus 3. It's the cation part of it. And so it's the electron deficient part. And so base acid. You seeing that? Now here, what's this one? Electron rich, electron deficient. Deficient, the ammonia, remember ammonia's got that lone pair of electrons right there. So the ammonia is supplying the electrons to make this complex ion here. But this is the electron deficient one, so I know that that's my Lewis acid. Okay? That's all you need to know for Lewis. Yes, ma'am.
And A is this reaction,
That would make it a kind of go a base going to right to left. Is that what you're saying?
so it can follow different definitions.
Well, no, again, usually we're looking left to right. Except for Bronsted, then we do the conjugate when it goes right to left. Bronsted is the only definition that has the conjugate acid base part of it.
I'm gonna get my sleep from this message.
In a minute.
What does
Please,
that
it's a
word
long
say?
walk.
What does what word say?
ADDU.
ADDUCT, adduct. Okay?
Yeah.
All right, well, you guys have a great weekend, and go Jags. And